All right, then we can move on because we now have an idea about what to study in vector and some of the basics of vector mathematics and what is a divergence, curl, and gradient, and some of the basic integration and like line integration, volume integration, surface integration, and all that. So we can move on to this section here, which is the magnetic field. And the best, so what I'm doing is I'm covering a lot of these things from Griffith, which is a very good book, and I definitely recommend that. So, so what is magnetostatics? We should have some introduction of electrostatic by now, in which a source of charge is addressed. So everything we deal with for a static charge is electrostatic. Now, the moment your charge is not static, it starts moving, then it becomes magnetostatic. Then we start dealing with magnetic field. So in like electrostatic, a static charge, a stationary charge can only produce electric field, whereas a moving charge can generate a magnetic field. That's something which is amazing, and that actually helped in creating a lot of things around us, like a lot of machineries, motors, fan, even a bike, everything largely uses this very mechanism. So it came from this idea that if like currents in opposite directions, if they come in a close vicinity, they start like repelling each other. The opposite is also true. Now that's because there is a magnetic field. We'll be knowing about magnetic field and how to calculate that in a little while. Meanwhile, just to understand that while you have a moving charge, a current that you already know, you basically deal with every day. So you have a current moving from like in a wire like in this direction. Then you have a magnetic field which is circling like this. So this is a schematic. If you have the current in this direction is your current, then this will be a force field because of the current, and this will be your field. Now why that? So the force field is basically Lorentz force. You'll be dealing with Lorentz force a lot of the times in physics problems. So it's basically, it's a vector because it's a force. Now it is given by the charge q with a cross product of the velocity, which is a vector v, and magnetic field b. Now if you also need to consider the electrostatic force, then the equation becomes, then we have to also include the electrostatic part. Now we have to also remember the magnetic forces do not work because it's a conservative force, or you can just put it vice versa. And it can be definitely put into a form of what? I'll cover that later maybe. Now, the way to prove it so in case of any particle, any charged particle, so if we consider the amount of work is force of the magnetic force and displacement dl. Now we can replace this one with this equation and this dot dl as v dt. Then you can automatically see, because of this v here and here, it becomes 0. So basically the work done is 0, and that also gives you that it's a conservative force. The reason because of the, reason for this one is v cross b is perpendicular to v here. Now cyclotron motion is, so like if we know about Large Hadron Colliders and LHCs, then the first like design of a like particle accelerator is basically cyclotron, in which we use this basic formula in where like the charged particle in a magnetic field. The principle is a charged particle in a magnetic field is circular, so the motion is circular. Whereas the magnetic force provides the centripetal acceleration. From this, we can actually find out the particle's mass or momentum by very simple experimental methods. So here is the force for the magnetic field, and this is the centripetal force, and they're equal, and that is how it's actually sustaining the cyclotron motion. Now, current is basically charge per unit time passing a given point. Now, if we have to write this magnetic force in terms of current, we can also do that. We're converting this charge in terms of current here. So for a wire with a current I, the Lorentz force becomes like this. Now I is a constant, then it's definitely a scalar, then you can bring it out. Now if we have to consider this one in terms of the surface current density, these are mostly for various kind of problems. You may not have the current directly, you may have to calculate surface current density. Then we use this kind of formula. Whereas like this one is a very small width, and this is the current within that. This could be also written in terms of the surface charge density and velocity v. So eventually what we have, Lorentz force, can be written in terms of this or like this. Similarly, if we consider the volume charge density, it can be written in terms of a small area and the total. So dividing the total current across this like small area, and then this formula changes in terms of charge density, which is rho, into the velocity. We've done much of these things in electronics. So the final equation you have for the force is this. This is a small example. A current I is uniformly distributed over a wire or circular cross section with radius a. Find the volume charge density. That's easy because you know the total current is I. Then you just divide it by the area. Now, suppose the charge current density in the wire is proportional to the distance of the axis. So it's giving you how J is related with this one. Now, we can actually put this I in terms of this one. Continuity equation is important in many cases, particularly for electronic applications. Now, as we already realized that I can be written in terms of volume charge density like this, because the definition of J. If we take a closed loop integration of this one, and by using one of the equations we discussed before, Green's theorem, we can convert it like this. We to convert it to a volume integration. Now, because charge is conserved, whatever flows out through the surface must come at the expense of the remaining inside. So for this part can be written in terms like this one, whereas rho is the charge density. So basically this part gives you that, like, the negative part actually reflects that the fact that the outwards flow decreases the charge that is left in the volume. So within that volume we have this one. So basically we are taking this part, we're converting it into volume within this equation. And now similarly, that is equal to this. So eventually these two are both on volume integration. I can eliminate that. What you have is this and this in terms of this one. This one is the continuity equation. Physically what it gives you, the left side gives you the, it's a divergence of J, so the current density, volume current density. So what happens is in divergence, it's basically the amount flowing out, the rate of flowing out of J, or current density. And whereas the right side gives you the reduction, the rate of reduction of rho, which is the volume charge density, which is evident. Now again, to understand, stationary charges produce electric field that are constant in time. Hence, these are called electrostatic. Steady currents produce magnetic field that are constant in time. So now we are dealing with magnetostatic or steady current. So steady current gives you constant magnetic fields which are not fluctuating. That's largely what we're dealing with in magnetostatic here. Now, clearly, when a steady current flows in a wire, its magnitude of current must be same all along the line. Otherwise, charge would be piling up somewhere and it wouldn't be a steady current. So in that case, your right side of the equation earlier becomes zero, like the change of charge density becomes zero. Hence, the continuity equation will be like this. So for a steady state current, your continuity equation becomes divergence of Z is equal to zero. So now, more or less, we understand a few good things about magnetic field, what it does, and the force because of the magnetic field. But this is the first time we're dealing with actually calculating the magnetic field. And we do that by Biot-Savart law. This law, this one, gives you, so if you have, say, like this kind of a delta R, delta L, this small part of a wire, which is a current carrying one, at a distance R, this point, if you want to calculate the force, the magnetic field, then which is in terms of R, this is your equation. Whereas mu0 is the permeability of free space, I is the current like going within this wire. This is your unit vector. R square is the distance. Can be written in terms of this. This has this value of 4 pi 10 power minus 7 Newton per ampere square. The definition of Tesla. Now, we don't need to deduct it right now, but we can calculate the magnetic field at a distance s from a long straight wire and a steady current I. So if we have a long wire, we don't know how long it is, and at a point P here, if we need to calculate the field, then We can calculate it by, like, we can just consider a small part here, a segment here. Let's do a segment here. And this is a wire segment, and we want to calculate the field for this segment at this point. At this point. So it can be immediately converted in terms of theta 1 and theta 2. So now we are not using Cartesian coordinates anymore. We're converting this one into a spherical coordinate. Then the Biot-Savart law gives you this. So we're converting the elements like L and S here in this term, and eventually you get this formula. Whereas S is the distance, direct distance, perpendicular distance from the wire. Theta 1 and theta 2 is this one and this one. Now, if you vary theta 1 and theta 2, you can actually change this length. And that's what we're doing in case of any straight wire segment. Like if you change the angle theta 1 and theta 2. For an infinite segment, what happens, like, so you have an infinitely long wire. So your theta 1 and theta 2 becomes minus pi by 2 and plus pi by 2. And from this equation, what you get is this value. So the field is inversely proportional to the distance from the wire, just like electric field of an infinite line charge. In the region below the wire, B points into the page, and in general, it circles around the wire in accordance with the right-hand rule stated earlier. Now for another application, let us find the force of attraction between two long parallel wires, a distance d apart, carrying current I1 and I2. Now we are dealing with two wires, 1 and 2. Both have a current, different one, and they are in a distance d apart. Now, so the field, because of 1 for 2, is mu 0 I1 2 pi d, which we calculated in the last page. Now, from Lorentz force rules, in terms of force law, from appropriate to the line currents, a force directed towards one will be I2. So this one will exert a force on this one, I2, then this one, and dl. So we are considering the whole length of this one. So it's a line integration. Now, in this case, because it is also so this one, if we consider the force per unit length, then this value becomes this. If the currents are anti-parallel, one up, one down, the force is repulsive, consistent again with the quantitative observation before. Find the magnetic field in the next example at a distance z above the center of a circular loop of radius r, which carries a steady current I. So now we are considering for this circle at distance z above the center of the circular loop of radius r of this one with a current I. What would be the magnetic field here? So similarly, by Biot-Savart rule, we have this, and we can calculate this value. So the magnetic field of a steady line current is given by Biot-Savart rule, And we can also write it in terms of the k vector, which is the, so we are changing this current in terms of surface current density and volume current density, depending on the problem. Now, the divergence and curl of the magnetic field is also something interesting. The magnetic field of an infinite straight wire is shown here. Now, the current is coming out of the page. At a glance, it is clear that the field is non-zero current. Now, in terms, we can write integral of b around a circular path of s. So if we consider a distance s and a circular path like this, center the wire, then this b dot, so a circular path for b dl. So we change the b in terms of the field we calculated from biosavart and dl. This becomes like this, and final result is this one, mu 0 into I. So here you're replacing this one by 2 pi s, which will be like actually cancelling out with this 2. So the answer is independent of s. That is because b decreases at the point at the same rate at the circumference increases. In fact, it doesn't have to be circle. Any old loop that encloses the wire would give the same answer. So if we use a cylindrical coordinate with the current flowing z, we basically have just the definition changing here. And if we do the same calculation for a cylindrical problem, we have the same result. Now this result is called Ampere's law. So this equation here, this one is called Ampere's law. So in case we have bundle of straight wires, each wire that passes through our loop contributing, like, will have a contribution of mu 0 I, and those outside will contribute nothing. The line integration will then be VDL of closed line integral will be mu 0 into I enclosed. I enclosed stands for the total current enclosed by the integration path. If the flow of the charge is represented by the volume current density Z, then the enclosed current becomes, in terms of the volume current density, this. With the integration taken over the surface bounded by the loop, we can apply the Stokes theorem. So we used Stokes theorem here to convert this one in terms of surface integration. So from here, we use Stokes theorem to do it this way in terms of surface. And we replace I here in terms of J, and we get this. And then we have the Ampere's law in terms of divergence. Or basically, it's a curl of B mu 0 into J. So it's a differential equation of the Ampere's law. Whereas this one is the integral form of this one. With the minimum labor, we find that actually obtain the general formula for curl of B. The derivation is seriously flawed. Let's go into it in a later stage. So from Biot-Savart law, we have this equation. Now, if we use this one to do a divergence of B, then we find something like this. That's basically, now that can be split in terms of like vector differentiation can be split like this. Now curl of J is 0 because J doesn't depend on the unprimed variations, and this is also 0. So what you have is this value, which is divergence of B becomes 0. So we now have the divergence of B equals to 0. When we deal with some more advanced concepts, this will be more clear. For now, divergence of B 0 also means that the existence of magnetic monopoles are not possible. So what we have is curl of B is between mu 0, mu 0 into 0. It's called Ampere's law in differential form. It can be converted to integral form by using Stokes' theorem again, and this gives you this thing. Just as Biot-Savart law plays a role in the magnetostatic that Coulomb's law assumes in electrostatic, so Ampere's law plays the same Gauss's law here. So in electrostatic you have Coulomb's law. Here you have, so in electrostatic, Coulomb's law gives you like can be calculated from Gauss law and vice versa. Here also Biot-Savart can be calculated from Ampere's law, or Ampere's law can be calculated from Biot-Savart law. So this seems to be a pretty interesting problem to try, which I discussed already in the earlier slides. Now, to do some applications, now these are pretty easy applications. Find a magnetic field at a distance s from a long straight wire carrying a steady current I. So we have a wire carrying a current I, and at a distance s, we calculate the magnetic field. Now we're using a closed line integration of B, and because the B has no dependence on the L, we can just find out this one, which becomes u0 into I. So B is this. You remember this was pretty difficult to do it in terms of Biot-Savart law, but this is far more easier here. And further apply it to calculate the magnetic field for a very long solenoid consisting of like many turns with a steady current I. And here we are replacing the surface current in terms of K. So in simple, what we have, the final result is the magnetic field becomes mu 0 I n inside the solenoid, somewhere here, and 0 outside it. It just depends on how you're actually considering your loop of like the Ampere's loop.